Hi everyone. This is a lecture about overfitting, cross-validation, and regularization in machine learning and deep learning both. So uh, today, as I said, I want to talk about overfitting, cross-validation, and regularization. So first off, some measures for a model, uh, learning model. So we have a function f which gets the ith input xi and outputs fi equals f of xi. So we have some learning model with and this learning model gets some input data xi and outputs some observation or some output of f of xi. So f is a mapping from xi to f of xi. We also can denote f of xi by fi for short. And however, this is an ideal model, this is an ideal model, but we don't have it. We don't have it. So we try to estimate it by f hat. So we wish to know the function, which we call it the true model. This true model, we don't have it, but we don't have access to it. Why? Because it is unknown. Okay. And this machine learning model, which is a true model, can do various tasks such as regression, classification, or anything. But we don't have it. We try to estimate that. So also the pure outputs, which are the f of xi's or fi's, true observations, fi's, are not available. Why? xi is available. So we have a data set of xi and also the labels or observations yi's, I from, for example, 1 to n. We have some data set. But f of xi, we don't have it. Why? Because we don't have f. As we don't have f, we also don't have fi's. So that's one thing. This is the true output. Fi's are the true outputs. Yi's are the outputs in the data set, or labels in the data set. And the output may be corrupted. The output or the labels in the data set might be corrupted with some additive noise, epsilon I. So we have yi's. We don't have fi's. Yi's might be the true fi's plus some noise. And this noise, we assume it is distributed Gaussian with mean 0 and variance sigma squared. And I denotes the ith data point. So we might have several of them, right? x1, x2, x3. And by the way, this true model, you can see it as an analogy. You can see it like the theory of ideas or theory of forms by Plato. Plato was an ancient Greek philosopher who had a theory of ideas saying that whatever we see in this world is just an image or an instance of some true true idea or true form in another world, maybe the world of ideas. And for example, when we see a rooster here, this is an instance of a true rooster in the world of ideas. Also human. For example, when you see Benjamin, when you see me, there is a true human in the world of ideas, but Benjamin is just an instance of that human in this world. So you can see there is some analogy with the Greek philosophy here too. So we don't have that true f, but we estimate it by f hat. Hopefully that f hat mimics the behavior of f. That's one thing. Okay. Now we have yi equals fi plus epsilon I, as we also see it in this figure. So fi plus some epsilon I gives us yi. And this epsilon I also is distributed Gaussian with mean 0 variance sigma squared. So its mean, so its expectation is 0 because its mean is 0, right? What is it? What about its second moment? So this is the first moment of epsilon I. This is the second moment of epsilon I. There is a formula for variance. Variance of a variable, such as epsilon I, equals expectational epsilon I squared minus expectation of epsilon I, that expectation is squared. This is a formula for variance. For the proof of this, you can see one of the session of preliminaries in my statistical machine learning course. So if we rearrange that, we'll have this, and so we'll have this. This second moment equals variance plus expectation squared. We know that this expectation is 0 because of we just saw it here. And this is also sigma squared because of the variance of the Gaussian. So we'll have sigma squared, right? Okay. And the true observation Fi also is not random. It is not random, we know, because randomness comes here as an additive noise, and it appears in Yi. It is not in Fi. So the expectation of Fi equals Fi because it's not random. The input training data, xi, I from 1 to n, and their corrupted observations or labels, yi, I from 1 to n, are available to us as a data set, right? We would like to approximate or estimate the true model by a model f hat. So we don't have access to f. Let's estimate that by f hat in order to estimate the observations from the input. So this f hat, if we input xi to this f hat, it gives us yi hat, right? And we hope that this yi hat is as close as possible to this yi. Of course, we don't have fi. We could hope that yi hat becomes very close to fi, but we don't have fi. At least we have yi's for the training data. For training data, if you feed the xi to the f hat, it gives us yi hat, and we hope that it's as close as possible to this yi, which is available, right? Okay. Calling the estimated observation by yi hat, I from 1 to n, at least for the training data, we want this to be as close as possible to yi, right, for the training data. So we have some training data points, xi, yi, and their labels yi's, I from 1 to n. If we feed xi to the machine learning model, it gives us, it outputs some yi hats. And we hope that this yi hat and yi are the same. So the machine learning model outputs the desired labels, right? Or observations. Okay, we train the model using the training data in order to estimate the true model. After training the model, it can be used to estimate the output of the model for both the training input and the unseen test input. So after training with the n data points and their observations, we can also test it, use it, evaluate it by the test data, which is unseen during the training phase. And let the number of test data points be m, right? Okay. And we'll have n outputs, predicted outputs for the training data, and m outputs for the predicted outputs for the test data. That's right. Okay. And as you see, we have training data, we have test data, and for each of which we have some predicted outputs. Okay. Here we denote the estimation of the observation of the ith instance yi hat. We also might call it fi hat. Okay. So here, do you remember in this figure? So we had fi, which we didn't have access to. We have yi, which is fi plus some noise. Yi is available for training data. Yi hat is just the output of the machine learning model, right? We might also denote it by fi hat, doesn't matter. So this is fi hat or yi hat, but this is fi. We don't have fi, we have yi for training data. The predicted output either for training or test data we denoted by yi hat or fi hat. Okay. So the model can be any machine learning model, such as regression or prediction or classification model, right? In regression, the model's estimation is continuous. The outputs are the continuous, or the label's observations are continuous, while in classification, the estimation is a member of a discrete set of possible observations. So whether the label's observations are continuous or discrete. Okay. The definitions of variance, bias, and mean squared error, MSE, can also be used for estimation of fi hat. There is a formula between mean squared error, variance, and bias, which is this. Mean squared error of a random variable equals variance of that variable plus bias of that variable squared. For the proof of this equation, please see preliminaries on probability in my statistical machine learning course, one of the initial sessions. Okay. We can rewrite this as this by saying that this is, let's have second root and a square. Also for this, let's have second root and a square. Then we can see this as a Pythagorean theorem as edges of some triangle. So we'll have this f, expectation of f hat and f hat here. So f is the true f hat is just estimation of f, and this is expectation of estimation of f, right? Or the mean of the mean of estimation. Also, this is bias of estimation. This is second root of this length is second root of mean squared error of estimation, and this length also is the second root of variance of estimation. This length is bias of estimation, right? Okay. Now, mean squared error of the estimation of the observations. So when I said to you that here, when I'm training the model, I said that I want yi hat for the training data points to be as close as possible to yi's. We said it in this sentence, right? In this sentence. We want it to be as close as possible in the training for the sake of training the model, right? Okay. So I think the first thing which came to your mind is using mean squared error. Let's minimize the mean squared error between yi and yi hat for the training data points. Okay. This is exactly what we are gonna do. So suppose we have an instance x0, y0. Consider some instance, okay? This instance, two cases might happen. This instance can be either a training data point or a test or validation data point. If it is a training data point, it has been used in the training phase for training the model. If it is a test or validation data point, it's not used for training the machine learning model. We'll cover both cases, okay? According to equation 1, what was equation 1? Let's go back and see. This was equation 1, where we said yi equals fi plus epsilon I. The labels, the training data points that we have are the true labels which you don't have plus some noise, all right? So here, now I can say it for the x0 and y0. So y0 equals f0 plus epsilon 0. So, okay. Assume the model's estimation of y0 is f0 hat. So we have x0, y0. This y0 is f0 plus epsilon 0. If we feed this x0 to the f hat, it gives us some y0 hat, some predicted output, right? Or also I may denoted by f0 hat. Doesn't matter. Y0 hat or f0 hat. Okay. Then we want to, this is y0. We want f0 hat to be as close as possible to y0. So we want to minimize the mean squared error between f0 hat, the predicted output, and the label in the dataset, y0. So this is mean squared error, right? f0 hat minus y0 squared expectation. Mean means expectation here, squared because of this, and error because of this difference, mean squared error. Okay. And now let's replace y0 with what we have in equation 5. So if we do that, we'll have expectation of f0 hat minus f0 minus epsilon 0. This is squared. Okay. Then consider this as a term and this as another term. I use this formula of binomial. A minus b squared. This is a squared plus b squared minus 2ab, right? So this is exactly what I'm using here. So the first term is squared plus the second term is squared minus 2, the first one, the second one, right? Okay. Now we know that expectation is a linear operator. So I can write it as expectation of the first term plus expectation of the second term plus expectation of the third term, right? Okay. Now what happens? So I'm repeating the first term here and also the last term here. But what was expectation of epsilon 0 squared? Or the second moment, what was the second moment of epsilon? We already proved that here in equation 2. In equation 2, we saw that expectation of noise squared is sigma squared, right? So let's replace it here. Okay. Now the mean squared has these terms. So 3 terms it has. 1, 2, 3. Now let's discuss on the third term in equation 6. So equation 6 is the mean squared error, right? This is the mean squared error. Now let's talk about the third term, which is this. According to equation 5, if I rearrange equation 5, epsilon 0 equals y0 minus f0, right? So I can replace epsilon 0 here by y0 minus f0. Also, I repeat f0 hat and f0 here. Okay. For calculation of this term, now we have 2 cases. Whether the instance x0, y0 is in the training set or it is not in the training set, meaning that in the second case, it's either in the validation set or test set. Okay. In other words, whether the instance was used to train the model or not. Case 1. Case 1. Assume the instance x0, y0 was not in the training set. So it's either in the validation set or the test set. So it wasn't used for training. In other words, y0 and x0 were not in the training set. Capital T showing the training set. This means that the estimation f0 hat is independent of the observation. So what was the observation? So we have x0, y0, right? We know that x0, if we feed it to the estimated model f hat, it gives us f0 hat or y0 hat, right? f0, y0. So if y0, x0, y0 were used for training the model, then the model estimated model would the output of the estimated model would be dependent on the data, training data. So if x0 and y0 were in the training data point, one of the training data points, then they had impacted f hat. Therefore, f0 hat would be dependent on y0 hat. But when x0 and y0 were not used for training f hat, then the output of this model, which is f0 hat, doesn't depend on y0 anymore. Therefore, in this case, where instance is not in the training set, okay, I can say y0 and f0 hat are independent. This is the symbol for being independent in mathematics, right? And probability. By the way, this is a notation for therefore in sorry. This is a notation for therefore in mathematics. Okay. Therefore, these two are independent. This implies that so these two are independent if I subtract f0 from the sides, they are also still independent. Note that f0 is not a random variable, right? F0 is not a random variable. F0 hat is a random variable. Okay, so I can subtract, and then I get so now this. Now let's consider the third term. Back to where we were in equation 7. I want to simplify third term in mean squared error, which is equation 7. Okay. As I said, these two terms in so we have multiplication of these two terms in the third term of mean squared error, but we saw that they are independent. So we know that if x and y are independent, then expectation of xy equals expectation of x, expectation of y. This is a formula. So if x and y are independent, then expectation of xy equals expectation of x, expectation of y. Okay. So for proof of this, you can see the preliminaries on probability in my statistical machine learning course. Okay. Then I can write it as multiplication of these two terms. So because these two terms are independent. Now let's look at this term, expectation of y0 minus f0. Okay. Here it is. As expectation is a linear operator, I can write it as expectation of y0 minus expectation of f0. Is that correct? Right. Okay. We know f0 is not a random variable, so I can write the second term, expectation of f0 as f0. We know that. What about the first term? Let's take a look at the first term, expectation of y0. What was y0? Equation 3. It was f0 plus some noise epsilon 0, right? If I take expectation from the sides of this, so we'll have expectation of y0 plus expectation of f0 plus expectation of epsilon 0. We saw that expectation of epsilon 0 is 0 because here, let me go back and show you where it was. Here in equation 2, we also showed that expectation of epsilon 0, epsilon I or epsilon 0 is 0 because epsilon I or here epsilon 0 is a Gaussian distribution with mean 0. Okay. Now let's go back to where we were. So this is 0. This term is 0. And we know that f0 is not a random variable. So expectation of f0 is f0, is itself. So it is f0. So I can replace expectation of y0 by f0. Also, as I said, expectation of f0 is f0 because f0 is not a random variable. So we'll have f0 minus f0, which is 0. So this term, which we simplified here, is 0. That's why I put it 0 here. 0 times everything here, which is not infinity, is 0, right? Okay. So basically, we showed that in case 1, where instance is not in the training set, the third term of mean squared error which was here, the third term, which is here, is 0. Therefore, mean squared error in that case will have only terms 1 and 2. So it is simplified to, equation 6 is simplified to this. This is mean squared error, right? Is expectation of f0 hat minus f0 squared plus sigma squared. And sigma squared is the variance of the noise for the labels. Do you remember? Okay. So I'm repeating that formula here that we found. Okay. Now, suppose the number of instances which were not in the training set is m, right? Do you remember I said we have m test data points or m validation data points, doesn't matter. Then we can approximate this expectation by Monte Carlo approximation. So Monte Carlo approximation says that when we have expectation of some random variable, I can replace it by 1 over the number of that variables, sample some data from that random variable, from the distribution of that random variable, set, for example, m of them, then you will have xi. This is Monte Carlo approximation. The more m, the better the approximation. Also, if we have a function of this, like expectation of g of x, you can see it as this. You can approximate it as g of xi. Okay, this is Monte Carlo approximation. Also, I introduced that in the preliminaries on probability in statistical machine learning course. Okay, you can see that. Then, what do we have? So I can approximate this first term by this 1 over m sigma I to m, and f0 now we have m of them, so I denote it by fi and yi. So fi hat I goes from 1 to m and yi. Also this by Monte Carlo approximation becomes this, right? So and also I'm repeating the third term here. So if I multiply the sides by m, then I'll have this summation plus m sigma squared, right? Okay. Now let's discuss these terms, these two terms. This term, which I have repeated here, what is it? It's the error between the predicted output, fi hat, and the label in the dataset, yi. What does it mean? It's actually an empirical error. Why? Because we are taking the error between predicted outputs and the labels of the dataset. However, the second term, which is this is the error between the predicted output and the true unknown label. So, which is fi. So one term in this term, the error is between fi hat predicted output and the labels in the dataset, which are corrupted by noise, right? However, in this term, this is the error between the predicted output and the true label, which we don't have. Okay. Therefore, I call this empirical error. I call this a true error. I hope to know the true error, but I never have it. I have the empirical error. I can calculate empirical error. I don't have the true error, right? Okay. I denote the empirical error by small error and the true error by capital error. So I can write it in this. So equation 9 becomes this. Empirical error equals the true error plus m sigma squared. If I rearrange this, I'll have, if I bring this to the other side, capital error equals a small error minus m squared, m sigma squared, okay? Sorry. So this equation is important for case 1, where the instance is not in the training set. So the true error, which we wish we knew, we don't know, is the empirical error, which we can calculate, minus m sigma squared. What is m? The number of points which are not in the training set. And sigma squared is the variance of the noise applied on the labels, right? Okay. And this m sigma squared is constant. So let's ignore that. It just applies some bias on the error for finding the true error. Let's ignore that. So we can say in this case, the empirical error is a good estimation of the true error, right? Because this term doesn't depend on the model. It depends on the noise, right? Which we can't do anything about. But it doesn't have any, this constant term doesn't have any f in it or fi hat in it. So we can say in this case, error is a good the empirical error is a good estimation of true error. And in this, when the data point is not in the training data set. That's why we can trust the test error. So whenever we report the test accuracy or the test error, we trust it in our experiments in industry, because we know that it wasn't used in the training set, and it's also a good estimation of the true error, right? Okay. Now case 2, when the instance is actually in the training set. In case 2, the instance, the data point is in the training set. So we use that. We use that in the training phase for training the model. Okay, for this case, we need to use a mathematical formula named Shor, which I introduced in this slide. Okay, consider a multivariate random variable z from z1 to zd. So it's a vector of z1 to zd. This is transpose, meaning that it's a column vector, okay? D-dimensional. Whose components, every component of this vector is an independent random variable with normal distribution. So each zi is a normal distribution mu I and sigma. If I put these mu i's, the means of the distributions of the zi's, next to each other to have a vector of mean, mu. Also, assume gz is a function on the random variable z. From G1 to GD transpose, okay? Assume so Zi, every element of Z is a Gaussian, has a Gaussian distribution with some means. We put the means together to have the vector of mean, mu. Also, GZ is a function on this random variable. Okay, from RD to RD. Okay. Then Stein's lemma, this is a lemma in mathematics, okay, states this. Expectation of Z minus mu transpose GZ, so the inner product between Z minus mu and GZ, if you take expectation, equals sigma squared. What was sigma? Sigma squared is the variance of the ZI. Okay. Sigma squared, summation of I from 1 to D, expectation of derivative of GI with respect to ZI. Okay. This is called Stein's unbiased risk estimator, or SHOR in short. Okay. For proof of equation 11, you can see our tutorial, the theory behind overfitting, cross-validation, regularization, bagging, and boosting. This is the title of our tutorial. Okay. If the random variable, so this equation 11 was for the multivariate random variable. If it is a univariate random variable, then it is simplified to be equation 12. So then we don't have transpose and distance anymore because it's just univariate. Expectation of Z minus mu GZ, because these are scalars, equals sigma squared expectation of derivative of GZ with respect to Z. We don't have summation because it's univariate, right? We are gonna use equation 12 for our case 2 when the instance is in the training set. Okay. I'm repeating that Shor formula for univariate this variable here. Now in the Shor formula for univariate variable, let's take z to be epsilon 0. Z, let it be epsilon 0. Mu to be 0, so I assume that why is mu 0? Because I took z to be epsilon 0 and I know that the mean of the noise is 0. Do you remember? In one of the initial slides of this slide deck, let me go back to show you. We assumed that the mean of noise is 0. Where was that? Here. In equation 2, we showed that. Okay. Now let's go back. So we take the random variable z to be epsilon, the noise. We know that its mean is 0, right? Also, gz is a function, right? Is a function on epsilon. And epsilon can be related to f0 hat. Why? Because f0 hat is the output of the predicted model, and we know y0 equals f0 plus epsilon. Y0 has impact on training the machine learning model, and f0 hat is outputted from the trained model. So I can say that this is related to epsilon, or the variable z here. Therefore, I can assume gz, which is a function on z, to be f0 hat minus f0. But you might be wondering why we are doing this, why we are taking z to be this and mu to be 0, mu to 0, because mu is the mean of epsilon, which is 0. But why do we take z to be epsilon and gz to be f0 hat minus f0? Because I want to, in the left-hand side of Shor, I want to make the third term of mean squared error. Recall what we had in mean squared error, the third term. Let me go back. Here, mean squared error had 3 terms, and for the third term, which was equation 7, I told you that I will consider 2 cases. We already talked about the case 1. Now in case 2, we want to make this and analyze it. It's similar to the left-hand side of Shor. We took the variables in a way that we make this equation 7, the third term of mean squared error. So what do we do? When we take this, put z to be epsilon 0, mu is 0, gz is f0 hat minus f0. Okay. Now, according to the right-hand side of Shor, we have this. So sigma squared, expectational derivative of f0 hat minus f0 with respect to epsilon 0, right? Okay. We know that derivative is a linear operator. Therefore, derivative of f0 hat minus f0 with respect to epsilon 0 can be broken into this. Derivative of f0 hat with respect to epsilon 0 minus expectation of f0 with respect to epsilon 0, right? Okay. Now, we know that this is 0. Why? Because f0 doesn't depend on the noise at all. F0 is the actual true model. Noise is added to F0 to make the Y0. So F0 is not dependent on epsilon 0. So its derivative with respect to noise is 0. Therefore, we get rid of the second term. We'll have sigma squared expectational derivative of F0 hat with respect to epsilon 0, right? That's correct. Okay. Now I have this. Let's use chain rule. So derivative of f0 hat with respect to epsilon 0 equals derivative of f0 hat with respect to y0 times derivative of y0 with respect to epsilon 0. All right, that's correct. Now recall that y0 was f0 plus epsilon 0, right? Therefore, derivative of y0 with respect to epsilon 0 is 1, because this is 1, right? Y0 is f0 plus 1 epsilon 0. So this term is 1. Therefore, it is simplified to this. Sigma squared expectation of f0 hat with respect derivative of f0 hat with respect to y0. Okay. Now let's put this back. This is the third term, right? Third term in mean squared error. So let's put it back in the mean squared error, which was equation 6. We'll have this, equation 13. So in a nutshell, what did we have? So we had mean squared error in equation 6, mean squared error between the predicted outputs and the labels in the data set. It had 3 terms. For the third term we discussed, which was equation 7, we discussed 2 cases. And when we solved and worked out the math, we saw that mean squared error for the case 1 becomes this, because the third term is 0 in case 1 where instance is not in the training set. However, if we solve the third term for the case 2 where instance is in the training set, the third term becomes this sigma squared expectation of derivative of f0 hat with respect to y0, and we use Shor for that, and we put it back, and equation 13 will be the mean squared error for case 2 where the data point is in the training set. Okay, I'm repeating it here again, what we found. Now again, like before, let's use Monte Carlo approximation for the expectations. And here now, suppose the number of training instances is n. Why don't I use the same m as before? So because now I'm assuming instance is in the training set. So I use the number of training data points, which is n. For the case 1, I assume that instance is not in the training set. So I use the number of test data points, which was m. Here I'm using n for Monte Carlo approximation because I assume I have n training data points. So these can be approximated by this 1 over n, summation of 1 to n. And again, I have several of them, so I replace subscript of 0 with I. Fi hat minus yi squared. Also, this term is replaced by this by Monte Carlo approximation. This term is repeated. For this term, I also use Monte Carlo approximation. Right? Okay, if I multiply the sides by n, then I will have this equation 14, right? Okay. Now, again, as before, this term is the difference, the error between the predicted output and the labels in the data set. So it's an empirical error. However, this is the error between the predicted output and the actual true labels, which we don't have. And that's the true error. So I denote again true error by capital error and the empirical error by a small error. So equation 14 is this, where I have these 2 errors. I wish to have the capital error, which is a true error, but I don't have it. I can calculate the small error, which is the empirical error. If I rearrange these terms, it meaning that I bring this to the other side. Also, I bring this to the other side. I will have this, equation 15. Okay, again, to recap, for case 1, the difference, the relation of true error and empirical error was equation 10, right here. But for case 2 where the instance is in the training data set, the relation between empirical error and true error is equation 15. As you see, this is a constant similar to what we had in the case 1. However, we have another term, which is a pain in the neck for the when instance is in the training set. And we will discuss what this term is actually. Okay, so this last term, which is a pain in the neck, it's a measure of complexity or overfitting of a model. Why? What does it mean? It's the derivative of predicted outputs with respect to labels. It means that if I'm in the training data point, in the training data set, if I move the ith training instance, move its label, observation, how much the model's estimation of that instance will change, right? And if it changes a lot, it means that it's very complex, very overfitted. If not, it means that it's not complex. An example is this. Consider in figure A and B here, this data point, which is colored green, and the other ones are black. All of these data points are training data points. And I assume I have fitted a linear regression model on these data points. So it's this. Okay, if I move this data point, green data point, its observation. So this is X and this is Y, right? Observation. It's observation a bit, so I move it down. How much does it is in the training data point, data set. How much does it affect or impact the linear regression model? A little bit, not too much. However, consider figures C and D, where it's not a linear regression anymore. It's a non-linear regression, and it's very overfitted. It's very complex. Okay. Now, let's move this training data point down a bit. Let's move its observation or label down a bit. You see that the whole model changed, the behavior of the model completely changed. It was going up, now it's going down. Because in this complex model or overfitted model, the model wanted to pass through all of the data points. So it has to pass through this moved point too. Therefore, its behavior is completely changed here. So this shows this derivative. For figure A and B, this complexity, this derivative, this term is a small. However, for figures C and D, this term is huge. Okay? This term is huge. Therefore, this term can be seen as a measure of complexity. Okay. For better understanding, suppose, as I said, linear. So linear model here is underfitted. These two cases, A and B, are underfitted. These two cases, C and D, are overfitted. Okay. There is a middle case scenario where we have a good fit. So underfit is bad. Overfit is also bad. A good fit. For example, in this case, maybe a good fit is something like this. Not passing through all of the data points, which is overfitting, not just a linear model, which is underfit. So here, as the data is kind of curvy, quadratic, for example, then maybe a quadratic thing is good enough, a good fit. Okay. So, according to this equation, in the case where the instance is in the training set, the empirical error, this is empirical error, which we can calculate. This is the true error, which we don't have. The empirical error is not a good estimation of the true error because of this pain in the neck term, which is a complexity, measure of complexity. And do you know what is the reason? Because we usually want to reduce the true error, right? For reducing we don't have the true error. So we have to reduce the empirical error. But when in the training, when you reduce the empirical error, after a while, when you are reducing the empirical error, the complexity goes up. So one of the terms goes down here, then the term of complexity goes up. So there's a trade-off. There's a trade-off. And you can't have a perfection here. You can't continue reducing the empirical error, hoping that the true error also goes down. No, because the complexity error goes up. Okay. Because the complexity error also goes up. And we will see that this behavior we'll see in a few slides that after a while of training, while you are reducing the empirical error, the complexity goes up and you overfit. And I think for understanding this in a better way, let's get a bit philosophical. So we know that in life, whenever you get something, you lose something. It's I think if you think about it, it's not possible. It's impossible that you get something and you don't lose anything. The least thing that you lose for obtaining something is your time or something, but you might lose other things too. Whenever you get something, you lose something. And I think this has been discussed, especially in Eastern philosophy, such as Buddhism, Hinduism, and Confucianism. They have discussed this a lot. So now also recall that Galileo said that the language of the world is mathematics, right? And I think he was true. He was right. Why? Because as we see, also physics explains the world, and physics is also in the language of mathematics. Now, according to that philosophy and what Galileo also discussed, it seems that we have the same trade-off in mathematics too. In mathematics also, whenever you get something, you lose something. And machine learning is nothing but mathematics, okay? So that's why in machine learning also, whenever you get something, you lose something. For example, uh, when you have a simple model, machine learning model, when you a good thing is that it's very fast, for example, right? It's very fast, but it can't work on big data or complex data. Maybe it can't handle nonlinearity much. Then, for example, neural networks were developed and they could handle nonlinearity and big data. So we got something. So we made the model nonlinear in order to handle nonlinear patterns of data, also be able to handle big data. But we must have lost something according to this philosophy. We must have lost something. It's impossible that we haven't lost something. And what have we lost? If you think about it, you will see that you have lost pacing or speed. Because now, for example, for training neural networks, you need a lot of time. Maybe some of them maybe take days or even months to be trained. But if it was a simple model, it would take several seconds or at most minutes to be trained. So that's one thing. Also here, you want to reduce empirical error. You're getting better and better. However, you are losing simplicity. So you are becoming more complex. And because of losing this simplicity and becoming more complex, the true error also is going up. So that's the thing between trade-offs. Now let's compare this with the case one where we didn't have that complexity term. So it was equation 10. In equation 10, empirical error was a good estimation of true error, and there is no pain in the neck term for complexity. And I think it makes sense because we are not using that for training. And as we are not using that for training, we are not modifying the complexity of the model. The complexity of the model changes by training. Okay, and that's why also in experiments and industry and whatever, whenever we say this is a test result, managers care about the test result. They don't care about training result. The training result is it needs to generalize well on the unseen test data. And why do they trust the test data? Because of this. Question 10 also says that empirical error for the test data or validation data, doesn't matter, which is not used in training, is a good estimation of the true error. So that's one thing which I wanted to discuss. Okay, great. So Now we talk about so we talked about the case 1 and case 2. Now let's talk about overfitting, underfitting, and generalization. So if the model is trained in an extremely simple way, that its estimation has low variance but high bias, then we'll have underfitting. An example is that we have several data points, for example, like this, and we just fit a line to them. It's extremely simple. It has low variance because the line doesn't change much, but it has high bias because you have a lot of errors between the data points and their predictions, right? So you have high bias, low variance, and it's very simple. The model is very simple. This is underfitting, okay? It's also called overgeneralization. On the other hand, if the model is trained in an extremely complex way, so that its estimation has high variance but low bias. An example is that the same data points that we have, for example, we pass from all of the data points, right? Then it has high variance. Why? Because it goes the line is going up and down a lot, but it has low bias because the error between the training points and their predictions is very small. This is called overfitting. Why is overfitting bad? Because it cannot generalize well. What if it in the a test data point which is unseen in the training phase comes, then here it will be awful, right? So we'll see some examples. So in underfitting, we have low variance, high bias, low complexity. However, in overfitting, we have high variance, low bias, and high complexity. For example, here in figures A and B, we have fitted a line, so it's just underfitting. It has low variance, but it has high bias. Low variance because it's a line, but high bias. There's a lot of error. Here in C and D, we have high variance, but low bias, and that's overfitting. So we need a fit between these two cases. Neither underfitting nor overfitting are good. Only good fit is good. Okay. So now let's talk about generalization. An example for underfitting, good fit, and overfitting is illustrated in this figure. A is underfit. It's just a line, for example. It's too simple. B is good fit because almost good. So it has low bias because its error is a small. Yes. It has low bias because its error is a small. Also high its bias is not too much. Also its variance is also not too much. It's not going back up and down a lot, the line I mean. So its bias is good, its variance is also good, almost. So it's a good fit. It's a good fit. This is underfit. It's low variance but high bias. This is overfit. C. Because it has high variance, low bias. We want something like this. So this almost performs almost good on both training and test data points. Overfit works very well on training data points, but very bad on test data points, which are not seen in the training phase. Underfit works bad on both training data points and testing data points. So underfit is awful. Overfit is good for training, but bad for test. Good fit works well for both training and test. The ability of the model is to estimate by the way, as this figure shows, in both underfitting and overfitting, the estimation of a test instance might be very weak, while in a good fit, the test instance, which is not seen in the training phase, is estimated well enough with a smaller error, okay? The ability of the model to estimate the unseen data, the unseen test data, also called out-of-sample data, right? So the ability of the model to estimate it well is called generalization. It means that the model generalizes to unseen data, okay? And overfit data doesn't have good generalization, right? The lack of generalization is the reason why both overfitting and underfitting, especially overfitting, is not acceptable, right? In overfitting, the training error or the empirical error is very small. The empirical error is very small, of course, because it's passing through all of the data training data points. While the true error is very bad. The error which even, for example, on the unseen data points, the test data points, the true error which can be seen as a test error too is awful. An example is this. Consider these figures, and this square point is a test data point. It's not seen in the training phase. Also mentioned here and here, okay? As you see in both underfit and overfit, its error is too much, right? However, in good fit, its error is small. That's why the good fit generalizes well to unseen data point, right? In other words, here, error is a small. Capital error, true error is almost as small too. Here, error is large. Capital error is also large. Here in overfit, empirical error on the training data point is too small, so even smaller than the good fit. However, its capital error, which is empirical error on the unseen data, is awful, is large, right? Okay. By the way, something also interesting. It's not just in the world of machine learning. In the real life also, we have underfit, overfit, and good fit. Assume in doing research, you don't know yet too much. You study, but you don't study well. You are underfitting yourself. Okay, you don't know things. You don't know resources. You don't know the algorithms. It's underfit. You read the researches a bit, different ideas. Then you reach a good fit. Okay, then in that time you can improvise and also have some ideas and these things. But you read further. You read further and read every single paper and all of the things, details. Then you overfit yourself. You overfit yourself. Then you can't improvise anymore. You can't have good ideas, because whenever you have an idea, you say, "Oh, by the way, this idea was repeated in that paper." No, this idea, no, this is repeated. I saw it in another paper. You can never come up with a new algorithm, because you can always think of some similar algorithms in the research area. So it's not just for machine learning, even in real life, not just studying, in different aspects of life, you can see we have this underfitting, good fit, and overfit. Okay. Cross-validation. In order to either find out until which complexity we should train to become a good fit and not become overfitted, or to tune the parameters of the model, we should use cross-validation. So for two reasons, we need cross-validation. Either we want to find good fit, we don't want to reach, so because we start from underfitting, we reach the good fit, we train and reach for good fit, And if we train further, we become overfitted. Okay, we know when to stop to become a good fit. Or you might have some hyperparameters in your algorithm. You want to tune them, find the best parameters of your model. Then you need cross-validation in these two cases. Okay, in cross-validation, we divide dataset D, assume we have a dataset D, in two partitions. One of them is training set, denoted by T, capital T here, and one of them is test set, denoted by R. Okay, where the union of these two is the whole dataset, and their intersection is 0. So it means that when you have a training dataset, D, you just divide it to two disjointed sets. One of them is training set and the other one is test set. Okay. The T is used for training the model. The training set is used for training the model. After the model is trained, then the test set is used for testing the performance of the model. Okay. And what you should report as a performance of your model is a test performance, test accuracy, test error, whatever. Because that shows whether your model generalizes well to unseen test data or not. Because you might perform very well on training data, but very bad on the test data, which means that you have overfitted. So we have different methods for cross-validation. Two most well-known methods for cross-validation are k-fold cross-validation and leave one out cross-validation, or short LOOCV. We are going to talk about them. Okay, so here in k-fold cross-validation, we randomly split the dataset D into k partitions, D1 to dk. Okay, we split them. Usually, we let the sizes be the same, almost the same. Also, their union should be D, and the intersection of each two of them is empty. So they don't have any intersection, they are disjointed. And when we have the union of them, it becomes the whole data set. So we divide, basically in simple words, we divide the data set into k disjointed sets. And this simple symbol denotes the cardinality of the set. Okay. Okay. Sometimes the data set D, sorry. Give me a sec. Okay. Sometimes the dataset D is shuffled before the cross-validation for better randomization. So we shuffle the dataset because we want to make it completely, we don't want to depend on the order of data points in the dataset, right? And that's one thing. Okay. Moreover, both simple random sampling without replacement and stratified sampling can be used for this splitting. So one approach is simple random sampling, or SRS, without replacement. So I have the data set, I randomly select one of them, put it in the set. Also, I don't replace it. I randomly select the second one, I put it in the set. So I by randomly sampling them without replacement, I just can make DK disjointed sets. Okay. Another way is a stratified sampling. What is a stratified sampling? Is just saying that let's when you have some data, let's make several clusters of data. These clusters are called strata. There's some strata of the data, and from each stratum, I guess, or each cluster, you sample, you do simple random sampling. So from each cluster, you sample. So in this way, you will have fair sampling from the clusters of data. This is called a stratified sampling. For more information, you can take a look at my tutorial named Sampling Algorithms from Survey Sampling to Monte Carlo Methods, Tutorial and Literature Review. This is its title, okay? You can use it for splitting or simple random sampling. So the k-fold cross-validation includes k iterations, where in each of them, one of the partitions is used in the test set, and the rest of data is used for training. For example, assume k is 3. Okay, so 1, 2, 3. Once I take 1 and 2 for train and 3 for test. Once I take 1 and 3 for train and 2 for test. Once I take 2 and 3 for train and 3 and 1 for test. So I take once in a while, I take one of the sets as a test and the rest as a train. So this is what we do in k-fold cross-validation. And then at the end, so we'll have one test accuracy or one test performance, whatever measure that you're using. You have some test performance for this one, some test performance for this one, some test performance for this one. So in this case, we will have 3 test performances. Then the total performance or the total estimation error for the test is the average. Then you take the average of these 3. Assume this gives you error 1, error 2, error 3. Then the error of total is 1/3 error 1 plus error 2 plus error 3. So we'll take an average of performance or average of error. We usually have k equals 2, 5, or 10. But k equals 10 is the most common in the literature. So we usually have 10-fold cross-validation. In the papers, when people don't do 10-fold cross-validation, for example, they do something weird, such as 3-fold or these 5-fold, these things, we usually get suspicious. Why? Why did they do that? Maybe in 10-fold cross-validation, they didn't perform well. So that's why default is usually 10-fold cross-validation. However, when the data is small, they might choose a smaller number for k in cross-validation. That's one thing. But usually when the data is small, people usually leave one out cross-validation, which we will introduce in a few slides. Okay. So the algorithm for k-fold cross-validation is this. So we randomly split D into k partitions with almost equal sizes, right? Then we have a for loop. We have a loop over these k splits, and then we take the partition k. So k goes from 1 to k, right? So in each loop, we take one of the sets from the data as a test, and the rest as a train. So this means this is subtract for the sets. So this basically means d minus r, d excluding r. So d excluding the test set is the training set. Okay. Then use the training set to train the model, and then use the trained model after training the model. Feed the test data to that for the sake of prediction, and then get the error. This true error, you can see it as a test error, because as we saw that do you remember, for when the data was test and was not in the training data set, the empirical error of the test was a good estimation of true error. Let me go back and show you. I think that is important to recall. My device is a bit slow, so I need to go slowly. Sorry about that. So here, in equation 10, here, we saw that in case 1, where when the instance was not in the training set, empirical error of the test was a good estimation of the training error. Therefore, I can see that of the empirical error was a good estimation of the true error. Therefore, I can see it as a true error. That's why I'm in there I'm denoting that as a true error. Okay, so now here we say that the true error for the kth iteration is this, and at the end we take the average of those true errors to give the average error or the total test error. Okay, this is k-fold cross-validation. Now leave one out cross-validation. In leave one out cross-validation, we iterate for the size of data set. Let it be n. So this, for example, how many data points do we have in our data set? N data points. Then we iterate for n times, and in each iteration we take one instance as the test. So the test size is only one. The test set will have only one data point, and the rest of the instances as the training set. You might be wondering why, because we usually use leave one out cross validation when the data set size is too small. When it is too small, then it's not feasible to have a test set with big size, because it means that the bigger the test set, the smaller the training set you will have, because this will be D, then R, this is T, right? The bigger you take R, the less you will have for training. Therefore, when D is small, you take R to be 1 and the rest to be training. So that's why it's called leave one out. Leave one of them out for the sake of to be the test set or validation. The rest of the instances as a training, but one of them as the test. The overall estimation error is the average test error of the iterations, like k-fold cross-validation. Okay. Usually, when the size of dataset is small, it is used to use the most of the dataset for training and test the model properly. Okay. The algorithm is this. So we have a for loop for n for the size of dataset, and we take one of the instances as a test and the rest as a train. Use the test to train the model, and then feed the test the test data point to the trained model. You get the error, and then at the end that you will return the average error of the test. Okay. Okay. There are some cheatings in machine learning. I'm gonna talk about that. That's important. So the test set and the training set should be disjoint. It means that they shouldn't have any overlap. Their intersection should be empty. Why? Otherwise, we are introducing the whole or a part of test instances to the model to learn them. If they are not disjointed, if the training set and the test sets are not disjointed, it means that what are we doing? We are using some or all of the test data points for the sake of training, and that's cheating. Why? Because in industry, for example, we are not supposed to have the test data points. So consider what is test. Test is it means that, for example, you wanna make something for traffic control, a camera which controls the traffic and sees the scene and controls the traffic lights, for example. Your company does that, and then you train the model in your company. You make the product, you give it to the ministry. The ministry puts that on the street, and then the testing starts. This is testing. When it's installed on the street, do you have access to that? So the test data is coming, right? But can you use that for training? It's out of your company. You don't have access to that. You already sold that, right? That's why I'm saying that when you are training in your company, for example, you're not supposed to have access to the test data. You might get some data from them for the sake of training, but test data comes in the future. Don't have them. Then for reporting the result to them, if you use some test data in your training, it means that you're already introducing them to your model for learning them. Of course, the model will perform well on that because you're cheating. You are, how should I say? You are leaking some information of your test to the training phase for training the model. It means that the model has already been introduced to them. Therefore, of course, it will perform well on them. However, whenever you wanna report on test set, remember this example of mine, which I said about the traffic data. Assume you are in your company and you are training something, and then you put some of the tests in the training data. Then ask yourself, question yourself, aren't I supposed to not have access to the test data? Because when it goes out, it is sold to the ministry, they will put it on the street, and then the test data comes. If we cheat now, of course, the minister will be happy. But when they put it on the street, it will work awful. We'll have a lot of accidents. Then the ministry will get angry at us. At first, when we are selling, they will be happy. They will say, oh, performance is well. But it was because of cheating. But when it goes and it is sold out, you will see it will work awful. But however, when you were testing in your company, if you actually test it without, you don't introduce the test data to the training phase, then you can claim that, yes, it is working well because it is generalizing on unseen data. So you can trust it to put it on the street. See, that's what I'm saying. Okay, of course, in the way the model will learn to estimate the test instances easier and better. However, in the real world applications, the test data is not available at the time of training. Therefore, if we mistakenly have some intersection between training and test data sets, it is referred to as cheating in machine learning. We call it cheating number 1 because we have cheating number 2 too. Okay, so this is cheating number 1. Validation set. In some cases, the model has some parameters which need to be determined. In this case, so for example, sometimes we have some hyperparameters. So the machine learning model usually has some learnable parameters. I'm not talking about learnable parameters. The learnable parameters are found by some optimization algorithm in order to do our task, such as classification, regression, or something. However, it might have some hyperparameters, which are some parameters determined by the user. They are not trained by optimization for the training on the training data. It's just some, how should I say, hyperparameters set by the user. Okay, and then in these cases they need to be determined, but the user doesn't know what to put for the hyperparameters. In this case, we can split the data D into 3 subsets: training data set T, test data set R, and validation set V. Okay. Usually the size of train is larger than test, and the size of train is also larger than validation. So usually the training set is larger than both test set and validation set. First, we want to find the best parameters. Okay. For this, the training set is used to train the model with different values of the parameters. So, for example, we have some hyperparameter, alpha, for example. Then this alpha can be between 0 and 1, for example. Okay. Then let's, so the range of alpha is between 0 and 1. Let's divide it into several steps. For example, alpha equals 0, alpha equals 0.1, alpha equals 0.2, until 0.9 and 1. So for each of these different values of the parameters, for every value of the parameters, after the model is trained, it is tested on the validation set. For each of them, we train the model on the training data set. Then we test it on the validation set. Okay? Not on the test set, on the validation set. This is performed for all desired values of the parameters. So again, assume you have alpha, you choose some possible values for alpha, such as 0. For simplicity, I choose smaller set, 0, half, and 1. Okay, then you will have a 4 alpha in the range, either it is 0 or half or 1. For each of them, you train your model with that alpha on the training set, right? And then evaluate your model on the val set. Okay. After this 4, you will see which of these alpha values gave a better performance on the validation set. Then you choose that alpha. Okay. What if you have two parameters, two hyperparameters? One of them is alpha, the other one is beta. And beta can be, for example, either 100, 200, 100 or 200, something like that. Then you will have a nested loop. For alpha equals 0, half, 1. For beta equals 100 and 200. Then train your model on T with that alpha and beta, and eval your model on the validations. After this, so you will store all of the validation performances for each of these alpha and beta. And then after this nested loop, you will see for which alpha and beta you will have the best performance on the validation set. Okay. And then you'll say, okay, I will choose that alpha and beta. So if you have several hyperparameters, you will have nested loops. Did you get it? Okay. So the parameter value or values resulting in the best estimation performance on the validation set is selected to be the value of that parameters. Then, so assume you do this, then choose alpha and beta with best performance on validation. What do you do? So assume this gives us alpha best and beta best. Okay. Then train your model again using training data with the parameters alpha best and beta best. Then at the end, test your data, test or eval your model on the test set. Then report this as the test performance. So what happened? Using some for loops or nested for loops, you found which parameters, hyperparameters are good to choose. Then using those best hyperparameters, you train your model. Then you evaluate your model on the test set and report that. Okay. So after finding the values of the parameters, the model is trained using the training set where the found parameter value is used. Then the model is tested on the test set. And the estimation performance is the average test over the cross-validation iterations. So again, you either do this or you can have a cross-validation for these two. So you will have several test performances and you can have an average test performance, right? Okay. We have cheating number 2, which we'll discuss in this slide. So in cross-validation with validation set, we divide, as I said, the data set into 3 sets: train, test, and val, and they shouldn't have any overlap. They should be disjointed, all of them. So assume this is D, then D will be divided into T, R, and V. Okay. The validation and test sets should be disjoint because the parameters of the model should not be optimized by testing on the test set. Do you agree? So assume, as I said, you can use in this last slide, I said, you can use cross validation, the nested for loops, for finding the best hyperparameters using validation set. See, here also V, using validations, right? Now my discussion is this. Can I replace this validation set with R, with test set? So can I use the test set for optimizing the hyperparameters, for finding the best hyperparameters? Of course not. Otherwise, that's cheating. Again, do you remember we said for training, we are not supposed to have access to the test data. Also, for finding the best hyperparameters, we are not supposed to have the test data. Test data comes after selling out our product. Why do you optimize your parameters using test set? This is called cheating number 2. See, in other words, in real world application, the training and validation sets are available, but the test set is not available yet. If we mistakenly have these, if some of the test is in the validation, it is referred to as cheating in machine learning, cheating number 2. And you cannot believe that many papers actually in research, and sometimes in also many things in the industry, people do this mistake, that sometimes they even get the test set as the validation set. So sometimes they mistakenly set V to equal to R. That's awful, you know. You are completely cheating. You're not supposed to have access to the test set for either tuning your hyperparameters or for training your model. This kind of mistake is very common in the literature, unfortunately, especially in the literature of deep learning. That's very common. Do you know why? Because in deep learning, it takes time to train the model, and people are lazy to do cross-validation for that. Because do you remember here in cross-validation in the for loop that we have here? Yes, in the cross-validation that, let me. Okay, so I was saying that in the deep learning especially, this cheating is very common. Do you know why? Because do you remember here in the for loop that we have for cross-validation, every loop, maybe in the nested loop, we need to train the model again from scratch. This trained model using the training data set and the chosen hyperparameters is time consuming for deep learning. That's why people usually don't do cross-validation for deep learning, and they just set the hyperparameters such as learning rate and these things to whatever works well on the test data. And don't you think it's cheating? You're not supposed to have access to the test data for setting your hyperparameters. Okay. In other words, of course, it will work well on the test data if you choose your hyperparameters based on your test data. You have some leak of information from this test data during your training. Of course, if you set your hyperparameters based on the validation data, then that's fine. If the validation and test data are disjointed. In deep learning, people usually don't do the cross-validation because it's time-consuming, the nested loop. They randomly do some grid search, some randomly choose some values and test it on the validation set. Those papers and this what those people are correct. That's correct. You can randomly choose some values on for the learning rate and these things for different hyperparameters, and then test on the validation set and see which one works well and choose that hyperparameter. However, you're not supposed to use test data for choosing those hyperparameters. That's one important thing. Okay. I'm saying that if you're lazy or if you don't have time to do the cross-validation nested loop, at least use the validation set for choosing your hyperparameters. Not the test set. Okay. Whereas some people optimize the parameters by testing on the test set without having a validation set. Actually, I have reviewed some papers, and in my comments as a reviewer to the authors of those papers, many papers have made this mistake, and I have said you need to redo this experiment by holding out some validation set and finding your best hyperparameters using the validation set, not the test set. You are using test set, and that's called cheating in machine learning. Okay, that's one thing. Moreover, the training and test sets should be disjoint. So here we said that the test and validation should be disjointed. Also in cheating number 1, which we discussed before, we said training and test should be disjointed. Otherwise, it's cheating number 1 because you're not supposed to have leak information from test to your training. Right? So we have 2 types of cheating. Either you use test in your training or you use test in your validation. On the other hand, the training and validation sets should be disjointed. So I'm justifying these 3 things in equation 21. So this is for cheating number 2. This is for cheating number 1. Now this one, train and validation set. Why should they be disjointed? Because if not, it is not cheating anymore, but it should not be done. And I will explain it. Because so cheating number 1 and cheating number 2, they are good for you for reporting your test accuracy, test performance, or for getting accepted your paper, or for making your manager happy in industry. But later it might perform awful when it is deployed. Okay. Or when somebody reads your paper and understand that you have cheated. However, the second one, which is this is bad for you when you want to report it to your manager or you want to publish. Why? Because if you have some of the validation in your training, then you will not understand whether you are overfitting or not. So one of the applications of the cross-validation is when to find out when we are getting overfitted and we don't continue. Do you remember we were talking about underfitting, good fit, and overfitting? So we can see the validation error and the training error. The training error always goes down. We'll see that in a few slides. But the validation error after the good fit goes up. It means that we are starting to overfit. If you have some overlap between your training and validation, you will not see that the validation error goes up. It will go down to because you have validation in your training. And you will not find out that you are overfitting. Of course, it will work bad on your test data. So these 2 are good for you, but it's cheating. This is bad for you. Okay. Now to have validation set in cross-validation, we usually first split data set into T prime and R, and then where T prime and R, they don't have intersection, but their union becomes a D, then we split the T prime into training and validation. In other words, we usually do this. We have D, we divide it into T prime and test. Then we get the T prime divided into T train and validation, right? This is basically this, but doing it in two steps. Okay. The algorithms of k-fold and leave one out cross validation can be modified accordingly to have validation set, because when I showed you, they didn't have validation set, but you can simply modify them to have validation set in them. In leave one out cross validation, we usually take validation set to be one. I'm to be one data point, because that's leave one out cross validation, right? Okay. Now justification of overfitting. So here, when the instance is not in the training set, the true error and the empirical error or test error behave differently. So which case is it? Do you remember? Yes. So let me. Okay, sorry. There was a typo in this slide, so I paused a bit and I thought about it. When the instance is actually in the training data set, okay, the true error and the test error behave differently. Why? Do you remember this? So here, let me go back. Again, as my device is slow, I need to do it slowly. I apologize. So here, recall what we had in this equation, in case 2, where instance, we said, is in the training set, okay? So we had this. When instance was not in the training set, true error was empirical error minus some m sigma squared. Do you remember? When it was in training set, true error is empirical error minus n sigma squared. This is similar. However, we have a pain in the neck term, which is based on the dependent on the complexity. So it's showing the complexity of the model, right? And we discussed that. We said that when we want to when we make the empirical error small, the complexity after a while goes up. This is exactly this figure that I'm gonna show is exactly showing this equation. This figure which we just saw. Here, figure A. So let me write down this equation for you here where we just saw. So we had this, we had error equals empirical. So this is true error and equals empirical error minus n sigma squared plus 2 sigma squared summation of 1 from I from 1 to n derivative of fi hat with respect to yi. And we said this is a measure of complexity. We discussed that, right? Okay. We said we want to reduce empirical error, hoping that the true error also goes down. However, after a while, the complexity goes up by reducing the empirical error. So let's see. This is empirical error. Okay. And we start training, the empirical error goes down. It is going down, going down. It always goes down on the training data, right? Because you are training on the training data. Of course, it will get better and better. It might have some oscillations, but its pattern goes down. Okay. At some point, so when you are reducing error, although you are increasing complexity, but the the impact of reducing error is more than impact of increasing complexity. Therefore, the true error also goes down. The true error also goes down until we reach some point which is a good fit. This is good fit, right? After that good fit, the increase of complexity dominates the reduction of empirical error. Therefore, the true error goes up. The true error goes up, although the empirical error is going down, but it is being dominated by the increase of complexity. Okay, and as you remember, this part is underfit, this part is overfit, and this is the good fit, which we should stop training. And in underfit, we have high bias, low variance. In overfit, we have low bias, high variance, right? And we have shown in figure B also that error is going down, empirical error, but the complexity is going up. So the summation of these two curves becomes this curve, ignoring this constant. So we have empirical error plus some complexity. So this is the curve of complexity going up. This is the curve of empirical error. If you sum these two curves, it becomes something like this. That's why this is the true error, behavior of true error. And as we saw, if for validation set or test set, which is not in the training set, the formula was this. Error was error. The true error was empirical error minus m sigma squared, which is, this is a constant. So we can say that error was a good estimate. Empirical error was a good estimation of true error. Therefore, we can see this true error as the error of validation or test, and we can see this error as the error of training. That's why when you start training, the error of training goes down, down, down. But at some point, it's also error of validation or test is going down. But at some point, although error of training is going down, error of validation or test goes up, starts going up. And at that point, we should stop. Okay. And we can also always check when we should stop. We can always check whenever we are training. We can always check whether the validation error is going up or not. If yes, then we stop. And that's also used in training neural networks, and that's called early stopping. That's widely used in neural network in machine learning. Okay, that's one thing. By the way, this axis, so this axis was error, right? This axis is, you can see it as either complexity, because complexity is going up in this direction, or you can see it as the iterations of the training. Why? Because the more you train, the more iterations you train, the more complex the model becomes. Okay. So if your machine learning model is trained iteratively, then you can see this axis as training iteration. Maybe your model is not trained iteratively. It is trained in one shot, but you can design it to be either less complex or more complex. Then you can see it as complexity, model complexity, something like this. So I think I already explained this slide. As I said, whether instance is not in training set or instance is in training set. This is a typo, sorry about that. Okay. Then I already explained that. Okay, now let's go to the next slide. So I said this is why we should not train a lot. This is why we should not train a lot on the training set, because the model will get too much fitted on the training set and it will lose its ability to generalize to new unseen data. This is the error on validation or on unseen data. This is the error on the training set, right? So the more we go here, the less generalization we have on unseen data. Figure A and equation 15 show that it is better to have, this is empty set. So we have to not have train overlap between training and validation, because otherwise, as I explained already, if we have some leak of information from validation to training set, we will not find out when we are overfitting. So in order to find out actually when we are starting to overfit, the intersection between training set and validation set should be empty. Okay. Otherwise, the validation error will also continue to decrease, like training, because there is overlap between training set and validation set. Equation 10 also explains that the error on validation and test set is good measure for true error. Yes, we already saw that here, because this is a constant. That is why we can use test or validation error in order to know until what stage we can train the model without overfitting. That's correct. Discussion of cheating in a nutshell. So we talked about two types of cheating. Now let's summarize them. If we have only training and test sets without validation set, so we only can talk about cheating number one. So the training and test sets should be disjointed. Otherwise, it's cheating number one. If we have training, test, and validation sets, then what happens? We'll have so the intersection of training and test should be empty. Otherwise, it's cheating number one. The intersection of validation and test set should be empty. Otherwise, it's cheating number two. The intersection of train and validation should be empty. Otherwise, we'll not find out when we are starting to overfit. It will be harmful for training, if not. Okay. So the first two items are advantages to the model's performance on test data, but that is cheating, and it may work awful after deployment. It may be disadvantages to future new test data, right? The third term, which is this, is disadvantages to the model's performance on test data, because we may not find out overfitting, or we may find it out late, right? And the generalization error will become worse. Therefore, it is better not to do it. Okay. Now regularization. So we can minimize the true error. So this is a true error, all right? Using optimization. So our goal is to minimize the true error. And we don't have access to true error. So we say that let's minimize the empirical error, something like that. But assume we want to minimize the true error, which is our goal, our desire. Do you remember the true error for when the data was in the training set? Because we want to train, right? We want to train. So we need to use the formula for the case where the data is in the training set. So we say that minimize true error. Now we can replace the true error by its formula that we found out. It is empirical error minus some constant plus some complexity term, which is a pain in the neck, right? Okay, as a term, this is a constant, we can drop it. So let's drop this. Then, by the way, when I say constant, it's constant with respect to the model's parameters, right? Because it has only N is the number of points, and sigma squared is the variance of noise applied to the labels. So it's not related to the estimated model at all. Calculation of this, which is a measure of complexity, is usually very difficult. Therefore, we usually use a penalty term in place of it, where the penalty increases as the complexity of the model increases. So we know that this is a measure of complexity, right? And the more the complex the model is, the more complex the model is, the more this term becomes. Therefore, let's replace it by a penalty term, which is also increasing with respect to complexity. So as long as we have a function which is increasing by the complexity, we can replace this or approximate this term with that function, where the penalty increases as the complexity of the model increases. And as we are minimizing this whole thing, it means that we will minimize that penalty. So we want to minimize the penalty on the complexity. We don't want the model to become too complex. We are having a penalty on that which is minimized. So we are minimizing the empirical error as well as the penalty. Give me a second. So I was saying, we are minimizing this. So I was saying, we are minimizing the empirical error as well as the complexity. This complexity term is hard. Let's replace it by a penalty on complexity. Therefore, the optimization can be written as a regularized optimization. So this is the true error, true objective function, equals the empirical error, some error that we measure, plus alpha some omega x, and this omega x is an increasing function with respect to complexity. This is the penalty term. Alpha is just a weight, a scalar, a positive scalar. So theta is the parameters of the cost function. X is the parameters, learnable parameters of the algorithm. J is the objective error to be minimized, the objective cost function, which is the empirical error to be minimized. Omega is the penalty function representing the complexity of the model. Alpha is the regularization parameter. It's greater than 0. It's positive. It's a scalar. It's called regularization parameter. This alpha is called regularization parameter. The whole thing is called, this is called regularization term, alpha omega x, or penalty or regularization term. The whole thing, J tilde, is called regularized objective function. So J is objective function or cost, but after adding this regularization term or this penalty, this becomes, the whole thing becomes regularized objective function or regularized cost function. Okay. Now, so I'm repeating what we had here. The penalty function can be, this penalty function can be different things such as L2 norm, L1 norm, and this function, which is increasing with respect to complexity, can be L2 norm. Why? For example, this can be like this. So this is the learnable parameter. And why is it increasing with respect to complexity? Because the more complex x becomes, the larger the L2 norm becomes. The more x, the larger x becomes, it means that the more complex it becomes, it will blow up the L2 norm, right? We can also have L1 norm. L21 norm is one type of norm, or it can be any function which is increasing by complexity of the model, or x, right? It can be a squared L2 norm, whatever. It needs to be a function. it shouldn't be decreasing with respect to complexity. It should be increasing, right? Because we are minimizing that. If we were maximizing it, then we had to say minus omega, because we always want to minimize the complexity, right? Okay. The L1 and L21 norms are usual for having a sparsity. So L1 norm can be used for sparsity. We will see why. Also, for more information, you can see my course on optimization techniques in my YouTube channel. I have explained that there too. So L1 and L21 norms can be used for sparsity. The sparsity is very effective. Why? So there is some principle in machine learning named Bethan sparsity or Bettin on sparsity. It's this. It says use a procedure that does well in sparse problems, since no procedure does well in dense problems. You can see references 7 and 13. So what is it saying? It's basically saying that assume I have an algorithm which is dense. Assume I have a sparse version of this dense algorithm. So I have the same algorithm once in dense version and once in a sparse version. Blindly, without looking at the results, blindly, without looking at the results, I will say I bet that the performance on the performance of the sparse model is better. So blindly, I bet that if you run the models and you test it on the test data points, you will see that usually the sparse model works better. Not always. Sometimes it's the other way around. The dense model works better. But the betting on sparsity says blindly, this usually happens, that the sparsity works better. That's one thing in, it is a principle, and Hastie and Tibshirani at Stanford University, they proposed that in their book, Elements of a Statistical Learning. Also, it can be explained in another way too. The effectiveness of sparsity can be also explained by Occam's razor. You can see reference 14, stating that Occam, by the way, was an ancient logician or philosopher. He mentioned that the simpler solutions are more likely to be correct than complex ones, or simplicity is a goal in itself. In other words, it says that when I have a phenomenon, assume I have a phenomenon, and this phenomenon is explained by two things. Two things explain the same phenomenon. I see which one is simpler. That one is more logical and rational. So I will choose that. The simpler explanation is the better explanation. This is Occam's razor. An example is that I'm hungry. Assume I'm hungry. So one reason is that I haven't eaten for a few hours. This is one reason. Another reason is that a magician or an alien came, which was invisible, sat next to me and tricked me and to become hungry suddenly. So these two both explain why I'm hungry. Which one is the better answer for my question? Why am I hungry? Of course, because I haven't eaten for a few hours. So there is no alien who made me hungry. So this is Occam's razor. Okay, this is Occam's razor. Now, what we are saying. So according to Occam's razor, sparse solutions are better because they're simpler, right? What do I mean by sparse, by the way? I mean that when some vector or some matrix is sparse, it means that most of it is zero, most of its elements are zero, and it has a few non-zero elements. That's a sparse. It's like a jungle which have a few trees in it, and most of it is a desert. That's a sparse. Dense means that you have a lot of trees in this jungle. And these trees might be small and large, but very few areas in this jungle are empty. This is dense jungle. Empty jungle, you don't, in most of the jungle, you don't have any tree. Most of it is a desert. That's dense. Okay. So Occam's razor says, according to Occam's razor, sparse models also work better. So we are minimizing the true error, J tilde, and not the empirical error, J. Okay. We are minimizing the whole thing, right? As discussed before, minimizing the empirical error results in overfitting. That's why we don't minimize just the cost function. We regularize it by complexity because we don't want to overfit. That's also an important sentence. Think about it. We don't just minimize J. We add some penalty term. There's a reason for that because we want to avoid overfitting. Therefore, regularization helps avoid overfitting. That's an important thing. L2 regularization. Okay. The L2 norm regularization is this. Minimize this J tilde, which is J plus this. So alpha is the regularization parameter, which is also a hyperparameter. You can set it. And we have this over 2 because this is squared L2 norm is x tilde x. When you take derivative, it will be 2x. I want this 2b to cancel by this 2. That's the reason. Okay. By the way, this regularization parameter alpha determines how much the penalty is important with respect to the actual cost function. So the smaller alpha, the less we care about the complexity or the penalty. The more alpha, the more we care about it. Okay. It shouldn't be too large, otherwise it will dominate the actual cost function. Okay. The L2 norm regularization is also referred to as ridge regression or Tikhonov regularization. Okay. Suppose X star is a minimizer of the J. Okay, so this is J, the empirical error. Suppose X star is this, therefore, as it is a minimizer of J, the derivative of J with respect to X at X star is 0, because when, so this is J, this is a minimizer, of course, the derivative at this point is 0 by first order optimality condition. We also saw that in high school. For finding the minimum of a function, take derivative, set it to 0. That's it. Okay, at X star. Now let's see the Taylor series expansion of J up to the second derivative at point X star. So I have J, I say J hat is just an approximation, Taylor series expansion, Taylor series approximation. It's almost approximately equal to J plus the first term of Taylor has gradient. The second the term of Taylor series has Hessian in it. Okay. Then, interestingly, we know that this term is 0 because of this. Note that we are considering the Taylor series at X star. This term is 0, then so it will be only this term and the Hessian term. Okay. Now I'm repeating that here. We were minimizing this. Okay. So now let's see the Taylor series approximation for the for J tilde. For J tilde. Sorry, let's use that. I apologize. So here, this J hat is a Taylor series approximation for J. Let's replace this J with its Taylor series approximation. So I'm repeating this here. This is J tilde, right? Now replace J hat or J hat by its Taylor series expansion, which is this. And we have some regularization term too. right? Okay. Now, by first order optimality condition, or what we had in high school, for finding the for minimization, this is an unconstrained optimization problem, right? Therefore, for minimization, I can take derivative, set it to 0, or by first order optimality condition of j tilde. So this is j tilde. Take derivative with respect to x, set it to 0. So the first term, but it has x star in it, so it becomes a constant with respect to x. It doesn't have any x in it. We have x star in it, so it's a constant now. It becomes 0. So the first term, its derivative becomes 0. The second term is quadratic with respect to x. Its derivative becomes h x minus x star. Okay, x dagger here, because I have put x dagger. I mean that it's the solution of this set into 0. Doesn't matter. See it as x minus x star. Okay, I'm denoting the solution of setting this derivative to 0 by x dagger. So, and also this term is quadratic with respect to x. Its derivative is alpha x, right? Set it to 0. Then what happens? We have hx here, alpha x here. Therefore, I can factor out these x here. So it will be h plus alpha I, identity matrix. I have minus hx star. I bring it to the right hand side. So I'll have hx star. Okay. Now I'm left multiplied both sides by this inverse, h plus alpha I inverse. So this term goes away. So x becomes h plus alpha I inverse hx star. This is the solution to this optimization problem. Okay. X dagger is the minimizer of j. Okay. Now, what do we do? I have explained that why this is 0, why this is 0 in this sentence. And question 27 makes sense. Why? Because if we set alpha to 0, what happens? If we set alpha to 0, x dagger, or the solution to this optimization problem, will be h inverse h x star. H inverse h is I, identity matrix. So it's x star. So x dagger becomes x star. What was x star? In the previous slide, we saw that. It's actually the solution to minimization of j. And that makes sense. If you set alpha to 0, there is no penalty term. So the minimizer of j is also the minimizer of j tilde. That's correct. Okay. We saw that. Also, as I said, if we set alpha to 0, the dagger becomes x star. This means that the minimizer of j tilde is the same as minimizer of j once we set alpha to 0. Okay. If we apply, now let's continue this solution that we found. Let's continue equation 27 here in equation here in this slide. We have Hessian term in that equation 27. Let's use eigenvalue decomposition on the Hessian matrix. U delta U transpose. U is the matrix of eigenvectors. Lambda or delta, is called lambda, sorry. Lambda is a diagonal matrix having the eigenvalues of Hessian matrix, okay? For more information on eigenvalue decomposition, you can see my lectures, preliminary lectures in either statistical machine learning course or deep learning course, okay? Then using the decomposition we use this in equation 27. So this was equation 27. I have repeated it here. So I'm gonna replace h. We have two h's here by the eigenvalue decomposition. I have this. Also, I have this. Right? Now let's see what happens. So as one of the properties of eigenvalue decomposition is that the eigenvector matrix U is orthogonal matrix. Therefore, UU transpose becomes UU inverse. And if we don't truncate the columns of U, so it is a square matrix, UU inverse is identity matrix. Therefore, I can add UU transpose here. Doesn't have any impact. It's identity matrix, right? Here I'm inserting some UU transpose. Okay. Now, as alpha here, alpha is a scalar. I can, in the multiplication, I can bring it back and forth. So I can bring it here. Okay. Then I factor out, left factor out. In these, consider these two terms. I left factor out U, right factor out U transpose. So I will have lambda plus alpha I in between. Okay. Then what happens? Then I use this formula. When we have A, B inverse, it will reorder them, reorder in the multiplication. So B inverse, A inverse. So I have inverse here. Therefore, I will have U transpose. By the way, U transpose equals U inverse. Why? Because U in eigenvalue decomposition is an orthogonal matrix. So U transpose, you can see it as U inverse. U inverse inverse becomes U. Then this term inverse, we have it here. Then this term inverse, which is here, U inverse. The rest is from here, U lambda, U transpose. Also have X star here. Okay. Then, interestingly, we have U inverse here, and U inverse U becomes identity matrix. So we can get rid of that. We'll have the rest of the terms here, also the previous terms here. Okay. So we have equation 29. We could simplify the solution X dagger by the eigenvalue decomposition of H. Okay. Now, equation 29 means that we are, what does it mean? What is U transpose X star? It's projection of X star onto the column space of U. For more information on this, see the preliminaries of my courses, Statistical Machine Learning and Deep Learning. They are on my YouTube channel. U transpose X is a projection of X star here onto the column space of U. If we didn't have this term in between, U transpose X star, so U transpose X star would project X star onto the column space of U. U would reconstruct that. So U transpose X star would reconstruct it. Again, for more information, see the preliminaries on my courses. Okay. However, we have a pain in the neck term here. Lambda plus alpha I inverse lambda. That means that it is before reconstruction, it is being manipulated by some term. So we project it onto the column space, we manipulate it, and then we reconstruct. You should also note that as we are not truncating the columns of U, this projection is not a projection onto a subspace. We are in the same space. You can see this projection as a rotation. So in the same space, we are just rotating. I have explained it more in preliminaries of statistical learning. So U transpose X, you can see it as projection onto column space, or you can see it as, if you don't truncate it, if U is a square matrix, it's like in the same space, you are rotating it. So basically, you are rotating it, you're manipulating it, and you're rotating it back. Okay. So we had this X dagger. Now we can have the following interpretations. If alpha equals 0, what happens? It means that there is no penalty term, right? set alpha to 0, then we'll have lambda inverse only, this rather than this term. Lambda inverse lambda becomes I, so we'll have UU transpose X star. By the way, U is an orthogonal matrix in eigenvalue decomposition, therefore we can see it as UU inverse X star. UU inverse is I because U is not truncated, it's a square matrix. And this is X star. X dagger equals X star, which makes sense because because as we talked about it, when we don't have any penalty term, J tilde here, J tilde becomes J. So the minimizer of J is the same as minimizer of J tilde. Okay. By the way, I want to briefly mention why when I'm saying that one note from linear algebra, I want to say that because I think it will be useful for you to know that. Whatever function we have, such as A inverse A is identity matrix. Okay. But A inverse is only identity matrix if A is a square matrix. What do I mean by a square matrix? It means that the number of rows and columns are the same. So A is, for example, D by D. If A is a rectangular matrix, this is always true. A inverse A is I. But A inverse will not be I. A inverse is I only if A is a square matrix. This is true for all matrices. However, if A is orthogonal, what do I mean by orthogonal? An orthogonal matrix, in an orthogonal matrix, the columns of that matrix are orthonormal. It means that their lengths are 1 and they're perpendicular to each other. Okay? Their inner product, the inner product of the columns is 0. Every 2 columns, the inner product is 0. So if A is orthogonal, then A transpose equals A inverse. Because of this, for an orthogonal matrix, A transpose A becomes A inverse A, and according to this equation, A inverse A becomes I. So A transpose A becomes I. What about AA transpose? AA transpose, because of this formula, becomes AA inverse, and it is only I if A, which was orthogonal, is not truncated. It's a square matrix. It's what do I mean by truncation? I mean, when we have a matrix A, we select some of its columns and we get rid of some of its columns. It means truncating that. If I don't truncate that, it means that I use all of its columns. For example, in eigenvalue decomposition, I know that U, for example here, I know that U is an orthogonal matrix, and if H is D by D, U is also D by D. So U is already a square matrix. If I use all of its columns, it means that I haven't truncated that. In this case, it's a square matrix. Therefore, both UU transpose and U transpose U equals I. However, if I select some of its columns and get rid of some of its columns, U transpose U is I. However, UU transpose is not I anymore. That's one. In parentheses, I said something about linear algebra, which I thought is important. Okay. Now, if alpha is not 0, this term, lambda plus alpha I inverse lambda. So here we talked about alpha equals 0. If alpha is not 0, this term, you can see it as this, because lambda is a diagonal matrix. Therefore, this also will be, lambda is diagonal, I is also diagonal. Lambda plus I inverse is also diagonal. Lambda is diagonal, so the whole thing is diagonal. And this becomes like this. Assume the diagonal elements of lambda are lambda 1 to lambda d. So we'll have lambda 1, for example, plus alpha 1 inverse. So therefore, we have this term in the denominator. And also the lambda in the numerator comes from this lambda, right? If you see it element-wise, it will be lambda over lambda plus alpha. Okay. Now let's talk about the elements one by one. Lambda I, for example, lambda j over lambda j plus alpha. If lambda j is much greater than alpha, we'll have this. Do you agree? Because the lambda j, limit of lambda j over lambda j plus alpha, where lambda j is very large, alpha is being dominated by lambda j in the denominator. Therefore, it's very similar to lambda j over lambda j is close to 1. Okay, so for the jth direction, in that case, we have this. Lambda plus alpha I inverse lambda becomes identity matrix for that direction. Therefore, x tilde, x dagger is almost the same as x star for that direction. We have d directions, right? We have d elements, d diagonal elements. Because x is d-dimensional. Okay, so for that direction, it will be this. So the solution of j and j tilde will be almost the same. X star, recall that x star was the solution of j. X dagger was the solution of j tilde. Okay, so this makes sense. Why does it make sense? Because lambda I or lambda j here, I think it should denote it by lambda j. Lambda j much greater than alpha in this case means that the jth direction of Hessian and thus the jth direction of j is large enough to be effective. Do you understand? Therefore, the penalty is roughly ignored with respect to it. So we have some penalty. But when lambda j is much greater than alpha, what was lambda? Was the eigenvalue of Hessian. Was the eigenvalue of Hessian. And Hessian was the Hessian matrix for what? For what? In the Taylor series expansion of J, empirical error, right? So when lambda is large, it means that J is actually important at that direction. Therefore, we should ignore the penalty for that direction. This is an important direction for this error. Therefore, this J tilde for that direction should be almost close to J. Right? Should be almost close to J. However, if lambda J for one of the directions is much less than alpha, alpha is great, then the limit of this becomes almost 0. So lambda J over lambda J plus alpha becomes almost 0. So for the Jth direction, we have this to be almost 0. Therefore, x dagger becomes almost 0 for that direction. This makes sense. Why? Because for this case, the jth direction of Hessian and thus the jth direction of J is small, and it should not be effective. So in other words, when lambda J is for some direction, lambda J is much greater than alpha, it means that the penalty J is important and J tilde needs to be similar to J, almost close to J. If for some direction lambda J is much less than alpha, it means that penalty should dominate that direction. Penalty should dominate the cost J in that direction. In one case, in this case, penalty should be ignored almost. In this case, penalty should be dominating. Okay. Therefore, the penalty shrinks that direction to almost 0. So in the case where penalty is important, dominating, it shrinks that direction to almost 0. That's the understanding of L2 norm, regularization. Therefore, L2 norm regularization keeps the effective directions, but shrinks the weak directions to close to zero. Do you see that? Okay. The following measure is referred to as effective number of parameters or degree of freedom. We just talked about it, lambda j over lambda j plus alpha. Now let's sum it over all of the directions. Okay, this is called degree of freedom or effective number of parameters because it counts the number of effective directions as discussed above. Moreover, this term or this term, these are the diagonal elements of this, right? It's called the shrinkage factor because it shrinks the weak directions. Okay, did you get it? By the way, this is also mentioned in the book Elements of Statistical Learning by Hastie and Tibshirani at Stanford University. L1 norm regularization. Okay. As explained before, sparsity is very useful and effective. Why? Because of Bettina sparsity principle, as well as what? As well as Occam's razor. Okay. If x1 to xd transpose, so d-dimensional. For having a sparsity, what do I mean by sparsity? Most of them to become zero, and only we have a few non-zero elements. We should use subset selection for regularization. So we minimize j tilde equals j plus alpha x0. What is subset selection? It's this, defined as this. So the penalty, I'm setting it to be x norm x0. It's defined as this, summation of number of elements which are not zero. So count of number of the count or the number of non-zero elements. So if x has, for example, 3 non-zero elements and the rest d minus 3 zero elements, then this quantity will be 3. Okay. This is L0 with quotation norm. Why? What is the reason of quotation? Because it's not a norm. It doesn't satisfy the properties of a norm. For more information on the properties of a norm, recall or refer to the properties preliminaries in my courses, statistical machine learning or deep learning. Okay. L0 norm counts the number of non-zero elements. So when we penalize it, it means that we want to have sparser solutions with many zero entries. When we minimize this, it means that we want more zero elements, right? Because it counts the non-zero elements. Okay, according to reference 16, the convex relaxation of L0 norm or subset selection is L1 norm. Okay, because L0 norm is not convex and is not a norm. So in order to make it a norm and also convex, the closest thing is L1 norm. So L1, we use L1 norm rather than L0 norm. This is called L1 regularization, also referred to as lasso. So lasso is short for least absolute shrinkage and selection operator. The first letters of these becomes lasso regularization, proposed by Tibshirani at Stanford University. Okay. Theory for L1 norm regularization. Let me rest a bit and I will come back. Okay. So we continue. We said we were talking about L1 norm lasso regularization. So we said different methods exist for solving optimization having L1 norm, such as proximal algorithm using soft thresholding, coordinate descent. You can see these references. For more information, you can see the lecture non-smooth optimization in my course optimization techniques. So I have thoroughly talked about different algorithms for solving non-smooth optimization in that lecture. So there are some methods like these. Here we explain solving the optimization using coordinate descent algorithm. And we will see at the end, we will end up with soft thresholding. Okay, so the idea of coordinate descent algorithm is similar to the idea of Gibbs sampling. So coordinate descent algorithm is as an optimization algorithm. It's saying that let's optimize for with respect to every coordinate one by one. And the idea is similar to Gibbs sampling. Gibbs sampling, if you are not aware of, in statistics, there are various ways for sampling from distributions, right? One of them is Gibbs sampling, which says that if we have a multivariate distribution, let's sample from one of the distributions conditioned on the other one of the dimensions, or in the multivariate distribution. So it has, for example, it has d dimensions, right? One by one, take one sample from one of the dimensions conditioned on the rest of the dimensions. This is called Gibbs sampling. And so as you see, the ideas are similar. So one coordinate descent is in the world of optimization. Gibbs sampling is in the world of statistics, but the ideas are similar. Okay, we work on dimensions of the variable one by one. Similar to what we did for obtaining equation 27, we have this. So do you remember? This was the cost, regularized cost, but we have L1 norm now. Again, we can approximation, and the term with gradient will be 0 because of the first order optimality condition, and we'll have only this and the Hessian term, and also this term with L1 norm now. For simplicity in deriving an interpretable expression, we assume that the Hessian matrix is diagonal. We assume that the Hessian matrix is diagonal for simplicity. Okay, and this assumption has been made also in the deep learning textbook of Goodfellow. Okay, for coordinate descent, we look at the jth coordinate or dimension. Let's take a look at that. So j tilde at xj, which is the jth dimension of x, right, equals j hat at xj plus alpha absolute value of xj. Why? Because norm of x, L1 norm equals j from 1 to d absolute value of xj. This is definition of L1 norm. For more information, you can see the preliminaries in my courses. Okay, so, but if you consider only the jth element, the summation goes away and you will have only absolute value. Okay, now let's, so j hat, this is j hat, right? The Taylor series approximation. So if you consider only the jth element, we'll have j of xj star plus this. So here we'll have xj minus xj star. Here we'll have also xj minus xj star. And as they are a scalar now, because we are considering only one of the dimensions, it becomes xj minus xj star squared. H also is a H, we assume that it's diagonal, therefore we can consider only hj, right? If we wouldn't assume H to be diagonal, then it wouldn't be like this. It would be more complicated. Okay. Then this also, the jth element is this. And yes, that's it. And by the way, this C is just the rest of the Taylor series approximation, which we ignore. Okay. Yes. No, here it says C is a constant term with respect to xj, not dependent on xj. Yeah, it's a constant. We don't care. We can. I think it can be seen as the rest of the terms that we ignore. That's fine. Okay. Let's take derivative with respect to xj. Why? Because we wanna optimize with respect to xj, jth dimension. right? In coordinate descent. Again, this according to first order optimality condition, what we had in high school. Take derivative, set it to 0. Take derivative of j tilde, sorry, with respect to xj. This we have j tilde here. So the first the first term is a constant with respect to xj. It doesn't have it has xj star as its input, so it's not dependent on xj anymore. So it's 0. The derivative with respect to xj is 0. This is quadratic with respect to xj, and its derivative will be 2. These 2 by 1/2 cancel each other, so we'll have xj minus xj star here, also hj, plus this absolute value of xj, its derivative is becomes sines, right? Why? This is absolute value of xj, right? This is the function absolute value of xj. When you take derivative with respect to xj, it becomes a sine. Here is 1, here is -1. That's why it becomes sine. The constant also is derivative is 0, and then we set it to 0. Okay, what happens? Let's rearrange the whole thing. So xj, I call the solution xj dagger, doesn't matter. It's just naming. Then also, by the way, we multiply the sides by 1/hj, so this goes away, and we'll have alpha over hj, and we take this to the right side, so it will be minus alpha over hj sine of xj. We also have xj star here. I'm just rearranging these to get this. And this, according to the sine function, we have 2 cases. Either xj is greater than 0, so this sign becomes +1. We have this. Or xj is less than 0, so this sign of xj becomes -1. So this minus becomes plus. This becomes xj star plus alpha over hj. And this function is called soft thresholding function. Interesting. It's defined as so I'm repeating the function here, and I'm plotting the soft thresholding here. Soft thresholding. I also have written it here. So what does it mean? So if xj is so here this is xj dagger, this is xj star, okay, and let me think. Yes. Okay, sorry about the pause here. So it's basic, by the way. When I say xj dagger, it's just naming. It was xj, right? It was xj. I just named the solution as xj dagger here. So this xj, here we have xj, also we have sine of xj. So these are the same thing. This is xj, this is also xj. So xj equals xj star minus alpha over hj sine of xj. Let this y-axis to be xj dagger or xj, doesn't matter. This is xj. The x-axis is xj star. Okay. Now, let's consider this case where xj is greater than 0. This. Then for this, it will be xj star minus 1 over hj. This is the line that I'm drawing on, right? This is exactly the line xj star minus 1 over alpha over hj. This is the intercept, right? Okay. Now let's consider where xj is less than 0. It will be xj star plus alpha over hj, and this is exactly this line that I'm drawing on. Okay. Now one case happens when remains. When xj is 0, what happens? This is exactly this line. When xj is 0. Because this is xj and xj is exactly 0. So y-axis is xj. So xj needs to be 0. So we'll have 3 pieces. One piece, the second piece, and the third piece. 1, 2, 3. Right? This function is called soft thresholding. And as you see, interestingly, for a region between minus alpha over hj and plus alpha over hj for xj star, it's setting xj to be 0, completely 0. For the rest, it's making it small. So in these regions 1 and 2, it's making it a small, it's penalizing, similar to what we had in L2 norm. L2 norm also was penalizing and making it small or shrinking in that. However, for some region 3, it's making it exactly to 0, setting it exactly to 0. That's why L1 norm makes it sparse. Many of the dimensions fall in this region and they exactly become 0. So this is the difference between L2 norm and L1 norm. So even in the parts which is not exactly 0, it penalizes that. It penalizes that and makes them smaller. But in some region, it makes them exactly 0. Again, we can see it. If in this case, the solution to the regularized problem, which is xj, is exactly 0. Recall that in L2 norm regularization, we shrank the weak solutions close to 0. However, here in L1 norm regularization, we are setting the weak solutions exactly to 0 because these are weak solutions, right? Xj star is absolute value is very small. We are setting them exactly to 0. That is why the solutions are relatively sparse in L1 norm regularization, sparse. In L1 norm regularization, as shown in this figure, even the strong solutions are a little shrunk. Even strong solutions are a little shrunk, like in region 1 and 2. The fact that we also had in L2 norm regularization. Okay. By the way, L1 norm regularization usually ends up in soft thresholding. Either you use proximal operator or you use coordinate descent optimization. You usually end up with soft thresholding. And I think in the course optimization techniques, I also proved that the proximal operator of L1 norm regularization is soft thresholding function. You can see that course in order to see the proofs why we see soft thresholding for L1 norm regularization usually, because in the terminology of optimization, projection of the solution onto L1 norm cone is soft thresholding. You can see that that course for interested audience. Okay, comparison of L2 norm and L1 norm regularization. Now let's compare L2. We talked about L2 norm and L1 norm regularization. Now let's compare them. Another intuition for why L1 norm regularization is sparse is illustrated here. It's credit for Tibshirani in 1996, reference 8, when he proposed lasso regularization in that paper. So you can see this. This is a unit ball for L2 norm. This is unit ball for L1 norm. For more information, see my optimization course. Okay. And then assume you have some cost function. So this is J. This is the penalty. This is also J. This is the penalty. So the whole thing together is J tilde, right? We want to minimize J, so we want to be close to this. This is if we want X, this is X star. So minimizes J. But this doesn't minimize J tilde. because J tilde also cares about this penalty. So where the penalty and this cost J touch each other, that's the solution for the J tilde, which is X dagger. Okay, so this is a 2D case, for example. And these are, by the way, the contours of the function. At each contour, the function value is the same. It's like a bowl, for example, here, right? And as you see, when we use L1 norm, it's like sharp diamond. And the probability that the cost touches one of the edges or one of the sharp vertices of this diamond is high. However, in L2 norm, it's like a sphere, hypersphere. Here, but by the way, when I say sphere, in mathematics, a sphere is just a ball without its interior. But in better language, I should say it's like a ball, because ball in mathematics is a sphere also its interior. Okay, so there is a difference between ball and a sphere in mathematics. So this is a ball, like a ball, but L1 norm is like a diamond. In L2 norm, the probability that it touches the ball here is very low. So usually one of the coordinates such as this is shrunk close to zero, but it's not exactly zero. However, here the probability that this touches exactly one of these is very high, and this becomes exactly zero. And now this is 2D case. Increase the dimensionality. You will have a diamond with a lot of, you should imagine it in multiple dimensions. You will have a diamond with a lot of sharp edges. It's like some diamond that you can't even have it in your hand. It has a lot of sharp edges. When the cast touches one of the vertices, one of the sharp vertices, many of the dimensions become zero. So here, one of them became zero, but then in that case, except one of them, maybe many of them become zero. That's why L1 norm regularization makes it a sparse. It sets many of the dimensions to zero. That's L1 norm regularization. This is a comparison credited to Tibshirani. Okay, now some acknowledgement. Some slides are inspired by the textbook by Hastie, Tibshirani, and Friedman. The Elements of Statistical Learning, Data Mining, Inference, and Prediction by Springer in 2009. This is a very important book which would discuss a lot of these things. Also, betting on sparsity principle was proposed here in this book. Another textbook suitable for sparsity in machine learning is this by Tibshirani, Wainwright, and Hastie at Stanford University, Statistical Learning with the Sparsity, the Lasso and Generalization, Chapman, CRC in 2015. Some slides are inspired by the lectures of Professor Ali Ghodsi at the University of Waterloo, Department of Statistics. See his YouTube channel. His YouTube channel is very good, especially I believe many of these were taught by Professor Ali Ghodsi too, but the part where we used Shor for justifying overfitting. Those explanations were proposed by Ali Ghodsi. I haven't seen it anywhere else. So Professor Ali Ghodsi, for the first time, proposed that in his lectures available on YouTube. You can see that. Also, some slides are inspired by the lectures of Professor Hoda Mohammadzadah at Sharif University of Technology in Iran, Department of Electrical Engineering. She taught from the textbook Elements of Statistical Learning, and many of the things also she taught us, and I acknowledge her. Also, some slides are based on our tutorial paper, The Theory Behind Overfitting, Cross-Validation, Regularization, Bagging, and Boosting tutorial. I strongly suggest that you read that paper. That basically goes through what we went through in this lecture. Okay, so, the references. So if I wanna remember the ones which are okay. This is Stein's lemma. This paper, estimation of the mean of a multivariate normal distribution in Annals of Statistics, one of the important journals, in 1981. This is our tutorial, the theory behind overfitting, cross-validation, regularization, bagging, and boosting tutorial. There is a survey on cross-validation procedures for model selection in 2010. Also, elements of sampling theory. It's a good book in 1974 about sampling algorithms. Do you remember we talked about simple random sampling and stratified sampling? Also, we have written a tutorial, sampling algorithms from survey sampling to Monte Carlo methods, tutorial and literature review. That also talks about simple random sampling, stratified sampling, Monte Carlo sampling, etc. There is a course, deep learning. There is the book, Deep Learning by Goodfellow, Bengio et al. And Courville in MIT Press. That also discusses some of the topics we mentioned here, such as the regularization. So the regularization, the shrinkage. Do you remember the shrinkage factor and these things? It has been mentioned in both in various things, such as in Elements of a Statistical Learning, also in Deep Learning book, also in my tutorial theory behind overfitting cross-validation, also in the lectures of Professor Ali Ghodsi, etc. So this is the book, Elements of a Statistical Learning, Data Mining, Inference, and Prediction by Friedman, Hastie, and Tibshirani in Springer. This is the paper of Tibshirani, Regression, Shrinkage, and Selection via the Lasso. This is for the paper proposing lasso regularization and lasso regression in Journal of Royal Statistical Society in 1996, a very important paper. This paper also discussed the example of diamond, unit balls of L1 norm and L2 norm. Least square optimization with L1 norm regularization. I think this is a good paper. And let me recall, if I can recall what this was for. Anyway, doesn't matter. Okay, L2 1 norm and its applications. Talking about L2 1 norm, which is a good paper. Convex optimization with sparsity inducing norms, 2011. I believe either this one, just give me a second. Where was that? In 50. Okay. No. Quarter 6. Okay. So convex optimization with the sparsity in that inducing norms. These are important papers you can take a look at for sparsity. Also optimization with the sparsity inducing penalties in 2012. There is a statistical learning with the sparsity, the lasso, and generalization. This is a very good book about the statistical learning in machine learning. Sparsity in machine learning. Also, there is a paper on the role of Occam's razor in knowledge discovery, Occam's razor in computer science, 1999. I think it's a good paper. The book of convex optimization by Boyd and van der Berg. I think this is a very good book on optimization, although it focuses on second order optimization and interior point method. This paper discusses that the convex relaxation of L0 norm is L1 norm for most large under determined systems of linear equations. The minimal L1 norm solution is also the sparsest solution by Donohoe in 2006. Also, this is proximal algorithms by Boyd and Parikh. This is kind of a survey or tutorial paper on proximal operators. I think it also proposes a proximal operator. I have discussed that, and I taught this in my course optimization techniques. So you can take a look at the proximal methods. Coordinate descent algorithms also talks a survey paper on coordinate descent methods in optimization. Coordinate descent algorithms for lasso penalized regression, 2008. Okay, and this is explaining the Gibbs sampler in 1992. I think for Gibbs sampling, you can take a look at that. Okay, thank you very much. I hope it was useful.